A very good morning and welcome everyone. Thank you for joining us at e-KLESF 2022. I'm Dr. Ong Kia-Ju from University Tunku Abdul Rahman Uttar. Today, IR Liu Chi Leong, Ricky, will be presenting a webinar titled High Supersonic Flight, How the Engineers Did It. IR Ricky is currently the head of engineer of a local corporate jet engineering service company. He's a registered professional engineer with the Board of Engineers Malaysia with 33 years of experience in the aircraft engineering industry. IR Ricky is also a fellow of AAET. Just a little housekeeping before we start. If you have any questions, please type them in the chat box. We will bring them up during the Q&A session at the end of this webinar. Dear participants, please sign your attendance in the link posted in the chat box. Without further delay, let us turn the time over to IR Ricky. Over to you.
Thank you, Dr. Ong. Good morning to everyone. Let me just put on my presentation slide. Hang on. Okay, I would like to confirm if all of you can see my slides. Can every one of you see my slides? Can you see the slides, Dr. Ong?
Yes, I'm able to see the slide.
Okay, all right, very good. Okay, very good morning to everyone. Thank you for inviting. Thank you for inviting me and to come and do this presentation. And I think this is the third time, or the third year that I'm doing this presentation. Last year, I think I did it from United States. Now, I really appreciate, especially this organizing committee for inviting AAET, ASEAN Academy of Engineering and Technology, for speakers in order to support, in order to support the Kuala Lumpur e-Science Fair webinar. I think this ESF is very important. The reason is because I think in Malaysia, a part of the development, in the Malaysian's part of development, we need a lot of engineers, we need a lot of technologies, and also we need a lot of technicians. My purpose and objective here today is to share with you some of the experience that I've gone through, especially the fun, the excitement, the excitement of being an engineer. And I hope that to encourage all of you, to actually take up the engineering and technological profession, because I felt that it is one of the best profession, very enjoyable profession that we can actually find. All right. What I'm going to cover today, I'm going to cover a little bit on the high supersonic flight. And I'm going to start off with a little bit of an introduction to the supersonic or the sonic flight. I'm going to share with you a little bit on the passion of the engineers. The spirit and the essence of engineers are actually very hard to talk it out unless you yourself are or you yourself is an engineer. I'm going to cover a little bit on the origin of supersonic flight. Where did we start? How did we start, and what did we use to actually start it? And then after that, we went to another stage of development. As engineers, we keep progressing the human race, in terms of technology, in terms of the betterment of humanity. So we keep on improving ourselves. The engineers pick up all the challenges, and then they develop better and better and better. And you will see throughout my slides, some of the technology and the engineers development that have actually progressed us as humanity until today. I'm going to cover also the other airplane, which is actually the SR-71. The SR-71 is actually a legend. It has already retired, and still nobody can make a similar plane like the SR-71. And also share a little bit on the destruction of the SR-71 technology. Why do certain governments have to destroy it? Yeah. And of course, I'm going to end with the conclusion. Yeah. Now, what you see here is that two major players on the left of the slides, two major players. One is the Bell Aircraft Company. The other one is actually Lockheed Martin. Yeah. Of course, there are a lot of other companies, but it all started with these two companies and also another couple of more companies. But I'm not able to, due to limited time, I am not able to share all the information, yeah, of all the companies. So I choose only two of these companies, yeah. Aviation industry is a highly regulated company, highly regulated industry. The presentation here it is very much, yeah, of general information and my own personal experience, yeah, what I have observed, the engineers that I've talked to, the research and the development factory or the plant that I've visited, all this, yeah, I gather the experience and I plan to share it with all of you today. The presentation is purely for knowledge purposes, and any part of this presentation, yeah, does not negate the current requirements and specification laid down, yeah. So don't say that, oh, Ricky said that, Ricky said this, the one can, this one can, Ricky say cannot, Ricky say can. Not what Ricky say is important. It is actually what the regulatory body says, what does the authority says, what does the aircraft manufacturer says. Those are the important compliance that industry players have to comply with. For me, I'm just sharing of information and my personal observation, yeah, does not represent anybody. I would also like to acknowledge, yeah, all the sources of the information that I'm sharing with you here. They are all accessible to you. They are not high secret. They are all accessible to you from the books, from the internet, from the media sources, and some of the records or even the presentation papers. What I'm doing, what I did is actually I compile it and then couple it with my observation and experience and made it into a slides, yeah, so that I can actually share with all of you. Hopefully, I'm able to inspire you all to actually consider taking up the engineering subjects, technological subjects, even science, any other science subjects, or even mathematics subjects. Yeah. Now, I'm not sure how many of you have seen a picture like this on the books, on the internet. I'm not sure how many of you have seen this. Now, this picture that you see here is actually what we call the correct one. The correct term is what we call sonic vapor cone. It is not sonic boom. Yeah. Sometimes you will see in the media, they say that this is the manifestation of the sonic boom. This is actually not the sonic boom. This is actually a sonic vapor cone as a result of the airplane flying, you know, at the transonic speed. Yeah, at the transonic speed, where the sudden drop in pressure behind the object, behind the machine, cause a condensation. Now, if you have studied science before, you will know condensation actually creates a vapor, and this is what we see in the fighter jets. Yeah, I'm not sure if you have been to see the air show in Subang, in the Subang airport. In my last 33 years of industry, practicing in the industry, I have actually watched quite a few air show, especially in Subang airport. Sometimes you do see this vapor cone, yeah, a little bit. Okay, so if you look at the bottom picture here, you will see the different speed of the airplane will have different effect on the air around you. Okay, air from non-compressible until it becomes compressible. So these are the problems that engineers have to think how to solve the problem. Yeah, and one of the major problem of the sonic shock wave, yeah, when the airplane flies on the speed of sound, or even higher speed of sound, more than the higher speed of sound, it is actually the shock wave actually can destroy the lift effectiveness of the airplane, destroy the airflow or block the airflow of the airplane, where your flight control surfaces has no effect. You cannot control the airplane anymore. That was one of the major problem that the engineers face when they designed the airplane. Well, they managed to overcome the problem, yeah. And how they overcome it, of course, we're going to talk a little bit as we go along. Yeah. Something that I think we need to know, we talk about Mach number very much. Yeah, Mach number. What exactly is the Mach number means? Mach 1 is actually the speed of sound. Yeah, Mach 1 is actually the speed of sound. Actually, the Mach number, it is a ratio of the object speed, yeah, the velocity of the plane or the object over the velocity of the sound. Yeah, velocity of the sound. So object speed over the speed of sound, then you will get your Mach number. So Mach 1 is basically your equivalent, the speed that you're traveling or the object that is traveling is equivalent to the speed of sound. But what I'm trying to share with you today, it is not just about sonic speed. I'm talking about high sonic speed. High sonic speed, definitely it is actually more than Mach 1, Mach 2, Mach 3 and above, we call it high sonic speed. But once you go into more than Mach 5, it becomes a hypersonic. So that is another different category of speed. So what I'm trying to share with you today is somewhere between Mach 1 to Mach 3 point something. Yeah, that's why I call it the high supersonic speed. Very interesting, because we started off with very low speed. Yeah, very low, probably 0.1 or 0.2 sonic speed. Until today, we are able to fly up to Mach 6, Mach 7. If you are talking about rocket, it is even much more faster, which I'm going to show it to you later. Yeah, just a comparison. Yeah, for the benefit of the participants here, just for comparison, what do you mean by Mach 1? Yeah, now Mach 1, we are talking of a speed of about 1,235 kilometers per hour, roughly. Yeah, because the Mach number changes when you are higher and also when you are actually lower on the sea level. It is actually more easier to achieve Mach 1 when you are at a high altitude. For example, when you are at the 70,000 feet or 80,000 feet, due to the lower temperature and pressure, you actually achieve Mach 1 at the lower speed compared to you are at the sea level. But generally, for reference purposes, so that you have an idea what we are talking about. So Mach 1, we are talking about 1,235 kilometers per hour. Now, when you are walking, yeah, when we are walking, our walking pace speed is about 8 kilometers per hour. Yeah, let's say we are just a general walk. We are not talking about the people who walk for the competition. We are just talking a general walk. A general walk will be about 8 kilometers per hour, and the Mach number, if you convert it, is 0.0065. It's very slow. Yeah, it's very slow. When we travel to Penang, yeah, when we travel to Penang on the car at 110 kilometers per hour, the Mach number is actually 0.09. Yeah. We talk about bullet train in Japan. My children just came back from Japan yesterday. So in Japan, we know that there is a bullet train, very high speed bullet train that is actually traveling at 320 kilometers per hour. And we are talking about the Mach 3, yeah, Mach 0.3, Mach 0.3, yeah. 737, my aircraft, where I'm rated on, can fly up to 850 kilometers per hour. 737, even though it can fly that fast, that also Mach 0.8, Mach 0.8. 747, which I'm also rated on, Mach 0.85. Yeah, when we go to London, yeah, we cruise at 40,000 feet or 37,000 feet or 39,000 feet. We are traveling on cruise. Yeah, we are traveling on at the Mach 0.85, and from Kuala Lumpur to London, we can reach London in about 12 hours. Now, in terms of business jet, yeah, business jets, I flew in this Citation 10 plus before. We reached in US, we reached the speed of Mach 0.935. Yeah, we are not at Mach 1, but our aircraft speed is actually reaching Mach 0.935. Feels a little bit different, a little bit, but not that much. But I can assure you, over the wing, yeah, over the wing, the airplane, the wing speed, the velocity of the air over the wing has actually exceeded Mach 1 already. Okay. The legendary airplane Bell X1, yeah, Bell X1. We are talking about the when it first broke the sound barrier, Mach 1.06, and that is the aircraft that I'm going to share a little bit so that we can know what were the problems and how the engineers did it. Why is the study of this the supersonic speed is so important? Why is it so important? Because it will lay the data and the knowledge that we gain from the X1 will lay the foundation for the future supersonic planes or even hypersonic planes. Concorde, where all of us know, it is traveling at a Mach, generally it's Mach 1.76. Sometimes they say they to travel at Mach 0.2, but it's about around 1.76 or 1.8. Yeah. The famous F-14 Tomcat. Not sure how many of you know about it. The legendary F-14 Tomcat can travel at the Mach 2.0, twice the speed. Now, imagine the first item that human being refer to as sonic speed, or better than the what they call it, speed of sound. It is actually the bullet. The bullet that human being created actually can travel at the Mach 2.3. Yeah. Mach 2.3. Okay, SR-71, Mach 3.2, the Blackbird. This is the second airplane that I'm going to talk about it. Now, the rocket that flies Neil Armstrong, yeah, on the Apollo program that goes to the moon, it is traveling at the Mach number of 20.2. Even then, at 20.2 on the Saturn V, yeah, Neil Armstrong took about 4 days to reach the moon. From Earth to moon, it took them about 4 days. We are talking about 20 times, yeah, 20.2 times the speed of sound. And then, of course, just a very quick reference, we always talk about the speed of light, yeah. When we talk about the speed of light, it is 847,000 Mach number. 847,000, yeah, Mach number, yeah. So this gives you a general idea what the speed is when we talks about the Mach number and related to kilometer per hour. Now, when we travel at the speed of sound, yeah, just have a look at it. From KL to Penang, it will only take 15 minutes. For us to drive to Penang, yeah, from KL, from my house, when I drive to Penang, it will actually take about 3.5 to 4 hours. I'm talking about complying to the speed limit, which is 110 kilometers per hour. It will take about 3.5 to 4 hours. But if you travel at Mach 1, we can reach Penang in actually 15 minutes. Now, if you have a fighter jet and you fly from KL to Penang, if you only fighter jet travel at Mach 2, it is only 7.5 minutes for you to reach Penang. You know, you try to boil the water, you know, a kettle of water. Before your kettle even boil, you already reach Penang already. Yeah. And if you travel on a SR-71, the Blackbird, from KL to Penang, it only takes 5 minutes to actually reach. Before even you sit down, you know, make your coffee, before you even sit down, it is already reached Penang. So the speed actually can benefit human being. Speed actually can bring convenience to the people. Speed actually can cause, you know, can actually come up with some safety, emergency procedures and all those. That is why humanity has to depend on the speed, you know, the velocity so that we can actually benefit on it. And who can actually make this speed achievable? Who can build the equipment that can actually achieve all these speeds to actually benefit the mankind? It is actually the engineers. So whenever humanity want to develop and evolve and improve in terms of advancing their technology, the quality of lifestyle, engineers actually plays a very important role. Yeah, very important role. Imagine your house don't have an aircon. Yeah, the engineers never ever design or build a design an aircon for us. How are we going to have a comfortable life at a very hot temperature? Yeah, so engineers has always been there for the benefit of mankind. It's a very noble profession. Yeah. Now this is also another picture for the benefit of the participants. We are now the airplane that we see flying nowadays, the fighter jets, the fast jets. We have come to the 5th generation already. Yeah, we have a 1st generation fighter jets. We have a 2nd generation fighter jets that you can see on this slide here. We have 3rd generation fighter jets. We have 4th generation fighter jets, and also we have a 5th generation fighter jets. I personally myself, I have actually touched the 3rd generation fighter jets. I've touched the 2nd generation. I've touched the 1st generation, 2nd generation, 3rd generation, 4th generation fighter jets. The 5th generation, because it is a stealth, highly secretive nature, I do not have a chance to actually touch this airplane or even view the plane at a very close distance. But the rest of the planes, 1st to the 4th generation, I have actually, in a way, I have actually touched and actually felt that airplane before. And I personally went and checked the some of the systems on the airplane. Now, if we want to talk about flights, there is these 2 brothers that we always have to appreciate. Now, these 2 brothers, I think some of us would have heard about it. They are the bicycle mechanics. They are not like you who are studying in Utah, you know, having a good lecturers, good lab for you to do your test. They are just bicycle mechanics who were very, very passionate about flying. That passion inside them make them create history in mankind, because that airplane that they built, that they designed and flew, that was the initial concept of how an airplane can fly successfully with man on board, with an engine on board, with its propulsion system. These 2 gentlemen, the Wilbur Wright and Orville Wright, these 2 brothers broke the myth that man can only fly with a glider. If you know earlier, and if you look at the history, Otto Lilienthal, the German engineers, has been trying to fly, fly so many times until he crashed his glider and died. So what happened is that these Wright brothers took the papers of Otto Lilienthal and then restudy the paper, make the correction, redo the calculation, and eventually came out with a Wright Flyer. And they were the first one to fly a control airplane, control airplane with a propulsion engine. So because glider, you have to depend on wind, you have to depend on height. But the brothers know, the Wright brothers put on an engine, design a wing, put in the flight controls, they put in the rudder, the elevator, and also the aileron. And that actually was the first starting point, how human being can fly safely. So that is why we need to acknowledge this, the 2 brothers. And if you can see here, the blueprint of the engines that the Wright brothers had, you can see here the hangar, where the Wright brothers actually built near the Kitty Hawk, where they actually flew. It's a very small hangar, and this flyer, they call it the Wright Flyer, the flying machine, actually damaged. Eventually it actually crashed and then damaged, and they did not repair it. And the crash unit is still in the museum in the US. Everybody can go and see it, even though the Wright brothers are not here anymore. So you can see they built their own engines, the Wright engines. It is only very small 12 horsepower engines. Yeah, it can't even take off by itself. It actually had to launch from a track, from a rail track, and it is actually producing about 90 pounds of thrust on it. That is the humble start of how man can fly with a machine. Yeah, they have a lot of broken bones. Yeah, they have a lot of broken bones, twisted knee and ankle and all those, all for the sake of humanity development. Yeah. Now moving forward, yeah, after the Wright brothers, the information that we have gathered, the sampling, yeah, the knowledge that we have gained during from the Wright flyers has actually moved, yeah, has actually moved the engineering to the next level. That means the engineers now, instead of flying on a Wright flyer, very low powered engine, they actually start to looking for the way to fly faster. Okay, now in this talk, because we are talking about sonic speed, we are talking about hypersonic speed, I will actually concentrate on the segment where they actually develop the supersonic airplanes. Yeah, after the Wright flyers, there are a lot of other planes that actually came along. You know, they have a lot of this Stratoforest, you know, the Boeing, the Douglas company, they came up with a lot of this piston powered engine. But here we are talking about the sonic speed airplane. Now, sonic speed airplane, it has to start from this engineer. Now, this engineer is called D. Beeler. Now, D. Beeler is actually the project engineer in charge on the XS1. XX1 means the X1 aircraft, where actually it was used to actually fly at sonic speed or even supersonic speed. Okay. Now, again, when humanity, when the army or when the nation wanted the high-speed airplane, yeah, they wanted a high-speed supersonic plane that human being can fly for the sake of humanity development, or even at times for the sake of protecting the nation. Who do they look for first? Do they look for the accountant? No, right? They don't. Do they go and look for the what they call it, financial people? No, they always look for the engineers first. So if you're talking about protecting a nation, protecting the country, you always, especially with the technology to be used to protect a country, to move a nation forward, they always have to go back to the engineers first. So engineers is always at the forefront in terms of moving the humanity forward, including the protecting of the nation, including, imagine people want to conquer our Malaysia, and then we can't even build our own, let's say our own protective weapon. How are we going to actually protect the nation? Correct or not? So it is always go back to the engineers, go back to the scientists, and then come up with a weapon or a defense equipment that can actually protect the nation. Always go back to the engineers. That is what I observed here. Now, Bell X1 that was designed by this D. Beeler, it is actually nicknamed, yeah? It is nicknamed called the glamorous Glennis. The purpose of it is actually to break through the sonic barrier, yeah, because, you know, after the Wright brothers, the plane flew faster and faster. Boeing built their own plane, Douglas built their own plane, Cessna Aircraft Company built their own planes, you know. But all these airplanes, there are thousands and thousands and thousands of them. None of the airplane can fly and break through the sound barrier. None. None. Okay. Why? Because when they try to fly towards the higher speed, airplane actually went out of control and crashed. So a lot of pilots, even the fighter pilots, a lot of the fighter pilots actually died, because during the war, when they flew the airplane and tried to achieve higher speed, it actually went into a situation where they actually cannot control the airplane. They felt a lot of vibration on the airplane, a lot of fluttering on the airplane, and if they try to roll the aileron, cannot roll, they try to actually pull the airplane out, it actually went into a aerodynamic stall and the aircraft crashed. So many people actually died. So debuiler has a responsibility, has a duty to find out, what are the barriers, what are the items, what are the difficulties, what are the challenges, how can we break through the sonic barrier. So in order to actually break through the sonic barrier, he has to build an airplane that can actually capture the data, and then at the same time the airplane has to fly on a supersonic speed or sonic speed. So he came out and designed with this airplane. Now this airplane is a very special plane. I think they only built about 6 or 9 of them. All of them are actually being used to actually test the sonic speed. It is also have one objective of whether human being, whether we human being can fly beyond the speed of sound. Today, today we know that of course we can. But remember, back in the 40s, back in the 30s, we don't have any computers. We wouldn't know. We know that Neil Armstrong, on the Apollo program, actually flew to the moon at the speed of 20 times the speed of sound, Mach 20. Why are we confident? Why are we able to be confident to fly in Mach 20? Because of this finding and the data that came from the Bell X1 onwards. So it actually went and see humans can go beyond the speed of sound. It concluded, and then it also reinforced the understanding of technological barriers, the sonic boom, the shock wave, the sonic shock wave. How are we going to overcome it? All the data were being gathered. Actually, if you look at this airplane, it is only a single seater. It's a very small plane, full of instrumentation and recorders, hundreds of kilograms of sensors, hundreds of kilograms of transmitters and data recorders. All these data recorders are actually all mechanical or analog recorders. So the engineers have came up with a lot of instrumentations to put on top inside this airplane. This airplane got no weapons, no nothing on. It just has a rocket engine, the rocket engines to actually make it fly as much as possible, as fast as possible. Even that also, it can only fly for about 2.5 minutes, 150 seconds only. That is the time frame, the window that they have to collect all the data that they can, so that the data gained back will be passed back to the engineers, will be passed back to the scientists, will be passed back to the researchers, and then everybody together work and study and then analyze and then come up with a solution. And all these are manual calculations. So being an engineer, if you are actually a person who have no issue with mathematics, then I think engineers is a very suitable position for you. Of course, nowadays we do manual calculation, especially when we are studying. But once you have worked out in the industry, usually it is all computed programs where the calculations are not difficult to actually do, because we have the programs for you to do the finite element analysis, your heat transfer rate and all those. All this actually has been there. But for engineers from the start, we have to be strong in our calculation. Our mathematical skills is important. So I feel very sad, especially when I see a person who has strong, very good strength in mathematical skills, but then they didn't take up engineering. That is something that I always feel sad, because engineers work depend a lot of calculations, and only good engineers who are able to do good calculations will come up with very, very effective results. Okay, so you can see here the X1 single seater, single seater. This is the cockpit. This airplane, you can find it in the museum in United States. If ever you have a chance to go to United States like me, I've been traveling to United States for many times. Every time I land at a particular state, I always check first before I arrive whether there is any aviation or aerospace museum there or not. Because if there is, I definitely will visit these museums and then take pictures and then see how the engineers did it, where now we don't see it anymore. The past engineers, they were having so much of limitation, no computer power, limited material, limited understanding, limited data about, you know, about characteristics, you know, and they managed to build the plane, you know. So that always amazed me. So design engineer D. Bieler is actually the first person who actually put on a trimmable horizontal stabilizer on the airplane. Today, if you fly on a 747, on a 737, on a 777, even on a 787, on an Airbus 330, 350, all these airplanes actually has a trimmable horizontal stabilizer, where the tail of the plane, the horizontal tail of the plane, can actually be moved. You know, either is a decrease in the angle of attack or increase in angle of attack. These ideas to control the attitude of the airplane came from D. Bieler's time, and that has a significant, significant impact to all the future flying machines, even till today. So his legacy has impacted our life and the way we fly today. Yeah. So this is a cockpit. You can see it is a very small, a lot of instrumentations. Yeah. But one thing, if you look at this cockpit here, you don't see the throttle like a modern airplane. You know, the throttle in the center pedestal of the airplane, in the modern airplanes, just like our car, the pilot can actually increase power or reduce power. But this cockpit, if you look at it, there is no such thing. Why? Because this airplane is powered by rocket engines. Rocket engines, at that time, you either switch it on or off only. Once you light up the rocket, it will continue to burn until you cut it off. It's not like, oh, let's increase a bit more power, increase a bit power, like our car throttle, no such thing. Yeah, but it has 4 chambers. You can light up chamber 1, chamber 2, chamber 3, and chamber 4 if you want maximum, or if you want slow speed, reduce, cut off all the 3 chambers, just maintain 1 chamber. It's only on and off on the chamber. Yeah. Now, the X1 program, in terms of learning, trying to learn about the sonic of the airplane, actually evolved into, from X1, it went to X2, it went to X3, eventually it went to X15. So you can see here, you can see here, there were hundreds of flights, hundreds and hundreds of flights being tested. X means experimental, X from X1 to X15, even today X47, all these are experimental planes that are being used to continuously develop higher technology so that the plane can travel even faster and faster, safer and safer. Okay, of course, at that during the 50s, we already achieved Mach 3. And all this data, all this data will become the references on all the airplane engineers or designers who want to develop supersonic planes, including the rockets, including the rockets. So there's a lot of achievement on the X program, including the, high altitude speed, Mach speed. Of course, the X2, they came up with a throttle rocket engine. Heat resistant construction, when we travel at a high speed, heat become an issue, because of the friction of the air with the fuselage. Later, I'm going to share with you a bit more on the heat generated because of high speed flight, how the engineers overcome it. That's one I will share with you. And also the first to explore the thermal ticket, the thermal layer that is around a supersonic plane. So all these data are gathered and captured actually for use for humanity development. Of course, a lot of pilots died during the X program, initial stages of X program. And also some engineers also died as well because during the testing, sometimes the engines explode. Yeah, and then they were actually taking the data, and then they sacrifice. Yeah, they sacrifice for the humanity. Yeah, engineers are very noble, very noble jobs. Yeah. Now, how they launch it? How they launch the B-20 X1? They require another airplane to carry the X1 airplane. Yeah, because the airplane is, the X1 are very heavy, you know, for the size, because it uses a steel alloy construction, and you know steels are very heavy. And why do they need to use steel? Because of the heat. You cannot use aluminum to make the fuselage of the airplane. You cannot use aluminum because the moment you reach Mach 1, Mach 2, Mach 3, the skin friction against the air will generate a lot of heat, and that will cause a lot of problem on the airplanes. So they have to use steel. Now, because it is a steel construction heavy plane, and at that time, the turbofan, during that time, the turbojet or the turbofan engines was not available or during the infant stage. So the fastest way to actually study this, the study of a sonic speed, is actually use the rocket engine, where you put in the fuel and then the oxidizer, and then after that you just light it up, and then it just continue to burn. Okay. Now the restriction is that it actually only have a very small 150 seconds to collect all the data required. You know, from the airplane speed of the B-29, the moment they drop the X1 down, and then the pilot in the cockpit will start the engine. Yeah, will switch on the rocket engines, maybe chamber 1, chamber 2, switch on chamber 3, and then switch on chamber 4, and they are supposed to fly, you know, control the airplane right up to about 43,000 feet, and then try to clock the Mach number, while at the same time the instruments actually being put to collect the data simultaneously. So it is actually a high risk, you know, for everyone, you know, for the engineers and including for the pilots. But there is one problem. These rocket engines are not sustainable, because you can only carry a small amount of fuel, and you only have about 150 seconds to 5 minutes to operate that airplane. So it's not sustainable. But for research purposes, they actually have to find an alternate ways, something that is sustainable, something that can fly for hours and hours, not just fly for 150 seconds and then cannot fly anymore because your fuel all finished up already. Yeah, so the engineers have to go to the next level after we have gathered the data from the supersonic flight. So all this will be used as a reference to build the next airplane, yeah, which I'm going to share with you afterwards. Yeah, so it uses a one reaction motors, XLR 11-RM-3-4 with 4 chambers. Yeah, so the maximum thrust of this rocket engine for that 150 seconds, it is only about 24,000, about 25,000 only. Very small power for 150 seconds. Okay. Now, because of it's not sustainable, but we have the data, so we need the engineers to continue to do the research. And we are very fortunate because why? We have this engineer called Clarence Johnson. Now, Clarence Johnson is, we actually call him Kelly Johnson, yeah, nickname, yeah. I don't know him, of course. I read his biography and all those. Kelly Johnson is actually from, he's actually from Michigan, Now, he is also another legend in the aerospace industry, especially in terms of supersonic flight. He designed the fighters, subsonic airplane, sonic airplanes, and supersonic airplanes. Of course, today we're going to focus on the Kelly Johnson's supersonic airplane, which is actually the Blackbird. Yeah. Now, this is actually the Blackbird. Now, if you look at the information here, 1964 to 1999, this is the time after the after the Bell X-1. Now, the Bell X-1 information that had been gathered, of course, among the engineers, among the American societies, the data are actually being accessible. So Kelly Johnson came up with this bird. They call it the Blackbird, that flies up to the speed of Mach 3.2, yeah, not with a rocket engine, with a turbojet engine. That means it is an air-breathing engine. As long as the atmospheric has air, even though it might be a little bit of air, the engine can sustain itself, can continue to fly. Unlike the rocket engine, once your fuel inside your fuselage is actually consumed completely, you don't have any source of power anymore. Whereas this one, as long as you have air, it can continue to burn, and it is actually powered by the Pratt & Whitney engines. I am actually rated on the Pratt & Whitney engines. It is one of the best engines that I've ever worked on. Yeah, Pratt & Whitney engines power this Blackbird, and it actually have a afterburner, and this afterburner can burn continuously to maintain the speed of 3.2. It can fly up to 85,000 feet, yeah, double the height of the X-1, yeah, double the height of X-1, and actually carries a lot of camera. Okay, now this is actually a spy plane. It has traveled around the world many times, and actually it actually has managed to capture a lot of pictures. Yeah. Okay. Now, where does Kelly Johnson start from? Kelly Johnson is actually the engineer who very passionate about airplane. Even before when he was a student, if you look at this picture here, this is actually at Michigan University, his university. At that time, he was just a student. He was still a student at that time. And they saw this Lockheed, this Electra plane, the original design, where it is being tested in his university wind tunnel. So he went and looked at the airplane, did a few mental calculations, apply a few principles of aerodynamics on this airplane, and he know that this airplane is not a stable plane, it's an unsafe plane. The knowledge that he has, the passion that he has in aerodynamics as an engineer, by looking at the airplane, he can actually know whether it's safe or not safe. And eventually, the Lockheed actually modified the airplane and make the famous Electra plane. Yeah, it is actually a H-tail plane. This is only a T-tail plane, very unstable. So Kelly Johnson came out, yeah, as a very junior engineer, come up with the airplane with the H-tail plane. Okay, this is his bird. All right. Kelly Johnson also developed a lot of other fighters. Yeah, we are talking about the fighters P-38 Lightning, and then Starfighters, and also the other spy plane on the U-2. All these are his ideas. So you can imagine becoming an engineer, you want to develop and defend a nation. How do you do it? It is by your engineering knowledge, application of your engineering knowledge for the nation. And that is what Kelly Johnson did. Yeah. Now, SR-71 was actually built in 1964. I mean, it flew from 1964 to 1999. There were 32 of it built. Yeah, flying at the speed of Mach 3.2. Yeah, Mach 3.2. Very high supersonic speed. Yeah, able to not one of the airplane ever been shot down by the enemy, and it actually overcome a lot of engineering problems. This design overcome a lot of engineering problems associated with heat. Yeah, not so much on the supersonic shockwave anymore. There is some shockwave issues, but then what they have gathered from the X-1 has been applied and actually overcome a lot of problems. But there were also other issues that the Kelly Johnson need to overcome. Now, on the left here, you will see a U-2 Dragon spy plane. Before the SR-71 came out, actually, this was actually the SR the U-2 spy plane that is still flying around even till today. This Kelly Johnson has already passed away already, yeah, but his airplane is still flying around. 100 over of it was built and used for high atmospheric research nowadays. No more for the not for the war, yeah. Now, SR-71 is where I'm going to focus on this talk on the next session. Now, why is there a circus tent on this slide here? If you see the slide here, this is a circus tent. Now, this is the tent, I mean a similar tent that Kelly Johnson built his airplane. You know, when the Skunk Works department, advanced program, airplane development program department was established, they don't have actually a special space on their own. Kelly Johnson was given the task, build an airplane faster than speed of sound, you know, 3 times the speed of sound, and then fly at very high altitude so that nobody can actually shoot you, and then build the airplane out. And he built it inside a tent. He did not even have a factory, a plant for himself. And that is how passionate that Kelly Johnson has. And the department is so famous, even until now, everybody knows it is a Skunk Works, yeah, under the Lockheed Martin, yeah. This is actually a division of an advanced development program. This is a picture. Nowadays, you can see it because this airplane, they don't build it anymore. The blueprint are all destroyed. You cannot find even the mold to build the airplane anymore. But this is a picture of the factory, how it was being built and assembled by the engineers, by the technician, and also by the technologists. Yeah, 30 over of them were built. Yeah. Now, because Kelly Johnson, remember just now I said, if you are strong in mathematics, yeah, if you are good in mathematics, one of the fun that you have is actually taking up the engineer's job, because you will use a lot of formulas to actually, to overcome and calculate a lot of problems and solve a lot of problems. Now, at that time, Kelly Johnson's time, they call it the Michigan rule, yeah, Michigan ruler, yeah. I'm sure many of you have not seen it, especially the younger generation, but the older generation will know, before the arrival of computers, yeah, before the arrival of computer program, they used a ruler called the slide rule. And here, when they slide on top of it, depending on the formulas that they use, they can actually find a lot of good answers and very accurate answers, and incorporate them into their design of the planes, design of the wings, design of the final element, design of so many things, the power, propulsion, and all those. Because the formula, the complex mathematical formulas, it is all there. It's just that you apply and use this rule. Yeah. So Kelly Johnson came at the time of using this ruler. Yeah. And a lot of senior engineers in Malaysia as well, especially those who have retired. Yeah. They were using this ruler when they were studying engineering last time. Nowadays, no, we use program. Yeah. We use SolidWorks, we use CATIA and all those. Yeah. Now, before I move on to the next slide, this is what I want to show you. If you look at the left here, this is the original Lockheed Martin designed the plane. And this is the design that came out from Kelly Johnson to have a safer Electra plane. Yeah. So this is a H-tail plane. This H-tail plane actually became a signature or a symbol of a Lockheed plane, and it is actually one of the safest feature, especially when you have an engine failure. This airplane is very much controlled compared to the left airplane. Yeah. Now, to be a good engineer, probably I just share a little bit here. We need to have strong engineering knowledge, excellent application of engineering principles. This is very important. You must love to solve problems. I don't know, how would you see problems? To me, problems to engineers is something like a puzzle. You know, people like to play puzzle, the word puzzle and all those. For engineers, when we see a problem, it becomes a puzzle. Like me, recently we have an engine that is under power, but all the parameters of the engine, whether it's during takeoff, during cruise, you know, during climb, during maximum continuous thrust, all the engine parameters are normal, but the pilot reported it as under power, you know, and you can see the airplane when it is taxiing on the ground, it is under power. It becomes a problem, but this problem become a puzzle to me. And that is the interesting part of being an engineer. It's just like solving a puzzle. It's very interesting. You will try to use all kinds of formulas, you know, and you try to understand revisit the principle that we have studied before and solve the problem, you know. So problem solving, yeah, you have to be innovative. Sometimes you have to use method 1 to test it, cannot, you have to use method 2. Yeah, you have to be innovative. And you also, there's a lot of curiosity. No, when you have curiosity, it makes life interesting, right? When there's no curiosity, it is always very dull, monotonous. But for an engineer, no. For an engineer, there's a lot of things that crops up that makes you think your mind, how come I never thought about it? Yeah. How come I never encountered this problem? Oh, maybe I should call my friend, an engineer in the US, and see what is his opinion. So there's a lot of curiosity that makes the life of an engineer never be boring one. I mean, if you believe it or not, never be boring one. All engineers who have worked through their phase, you will know one. Afterwards, you can see in the conclusion remarks what Kelly Johnson say. We actually match, yeah. Both of us actually, we match each other in terms of the interesting job of an engineer. As an engineer, you need to have attention to detail. You need to have a mathematical capability. We are not asking you to be super good in mathematics, but at least, yeah, an average mathematics skills, you should be able to, you know, to be a good engineer. And also teamwork. You can never work alone. Engineers can never work alone. You have to work with the pilots. Like for me, I have to work with the pilots. I have to work with the technicians. I have to work with the technologies. I have to work with a lot of people. So teamwork is always there for an engineer. So remember these characteristics to be an engineer. Very interesting, I can tell you. Now, these are the SR-71. If you look at it, the diagram here is very futuristic, very interesting. Look at the engines, is so long, yeah, and the shape of the delta wing, and you can actually hardly see the wing. You can see the engines more than the wing, isn't it? If you look at here, on the side here, it's more engine area, you know, you can hardly see the complete wing. It's very small and stuck, yeah. Now, I mentioned earlier, how did Kelly Johnson overcome? If this airplane flies at Mach 3.2, yeah, Mach 3.2, the heat generated on the fuselage, on the cowlings, it will expand one. So when this SR-71 flies at Mach 3.2, it can extend, the length of the airplane can extend as much as 6 inches or even half a feet. That is a lot, you know. That is a lot. Your wing might even get a little bit expanded. How do you counter for this expansion? Otherwise, your skin will be under stress. Right? It already has a heat stress, plus the expansion. Now you even have a tensile stress. You know, all this, how do you overcome it? So if you look at the wing design here, you can see all these lines here. This is what Kelly Johnson incorporated. When it is expanded, it will become flattened. When the heat is being, if the wing is hot, it will become flattened and you don't see it, you don't see the line anymore. And the airplane flies perfectly. Simple solution, but then how many have actually thought about it? Yeah, how many have actually thought about it? Engineers, yeah, can mix complex problem into simple solution. That's our joy, yeah. This is also another view of the plane. So if you come from the side view, there is actually two seater. You can see here the second seater, which is actually the navigator. The pilot is actually at the front, yeah. Pilot is actually at the front. And this is the engines. It's a J58 Pratt & Whitney engines. And this spike here, the spike cone here, can go in and out, can retract and extend. actually to counter, remember I said the shock wave is very damaging to the airplane one. So how did they overcome it? They control the shock wave so that it does not come to the detrimental situation where your engines lost the function and your airplane goes into an aerodynamic high-speed sonic stall. Yeah. Okay. Now, steam gauges. Yeah, we call this steam gauges. SR-71 was built in the 50s, started to fly on the 60s, and you can see inside here all the analog gauges to monitor the whole system of the airplane, where the pilot monitor, where the engineers have actually incorporated the switches, control switches, all in the cockpit. So you can imagine the amount of system that actually we have actually interfaced and built into the SR-71. And every one of the switch, the pilot needs to know, the engineers need to know in order to fly this airplane safely. Now, we want to go into the Mach 3.2. We want to go into high supersonic speed. You don't go blindly, man. Correct or not? We cannot just go blindly. Otherwise, you will be in danger. So the engineers built all these instruments, including the control column here at the center. You can see in this engine here, on the left-hand side, if you see my arrow here, that is actually the throttle quadrant. Now you can control the power, low power, middle power, climb power, thrust power, max takeoff power, everything. Whereas the rocket engine just now, the X1 cannot. So the engineers has evolved the design in such a way that, okay, we will thank you for your data, thank you for your information. I'm now changing some of the information that you have and incorporate it into SR-71. And this is what you see. Yeah. There is also a trainer version for the SR-71. You can see there's only one at the front, one at the back. Is actually to train the pilots, yeah, to train the SR-71 pilots. It's very hard to be a SR-71 pilots. Very, very difficult. Number one, you have to have minimum 10 years of experience. Number two, just the classes alone, to fly this machine is 6 months. And practical itself is also 6 months. 1 year of training before you are even qualified. Yeah, a 10 years experienced pilot can actually fly a SR-71. Yeah, you can see it. I have seen it. I've touched it. Yeah, it's a marvel. I've seen it a few times in the Aviation Museum in the US. It is a beautiful plane and it is a legend. Yeah, when you look at this airplane, you remember the engineers who actually make this possible. Yeah. 85,000 feet, yeah, it can fly at 85,000 feet, which is actually about 25 kilometers, with the ambient temperature of -55 degrees C, and only an atmospheric pressure of 0.4 psi. Yeah, on our ground level here, we have about 14.7 psi on ground here. But as the SR-71 fly up to 85,000 feet, the air is so thin. How are you going to get your power? How are you going to get your power from the engine? But the J58 has been designed to be able to continuously produce power as long there is an air, even though it is only an ambient pressure of 0.4 psi, you will be able to have sustained combustion inside your turbojet engine. Yeah, this is a turbojet engine. It is not a rocket engine. It is a turbojet engine. Another view of SR-71. Yeah, another view of SR-71. Remember, I said 32 of them. Out of 32, how many actually crashed? Anybody can guess? I mean 36 of them. Actually, 12 have crashed. 12 have crashed because it is not easy to fly this SR-71. None of it was shot down by the enemies. Every time the enemy tried to shoot this airplane, they have difficulty because it's flying too high, 85,000 feet. And even when the enemy approach this airplane, all this airplane has to do is put on the speed and fly at Mach 3.2, because there's no other plane that can catch up with this airplane in the world at that time. Yeah, Mach 3.2, no other plane can catch up. It's flying too fast. Yep. This is the plane where the pilot goes up, SR-71. Yeah. Remember the engineers, even though they developed the technology, yeah, for the high supersonic airplane, but the pilot itself also need to have protection. So this is the pilot that actually wears the astronaut level kind of suit, where the suit itself is their living environment. 85,000 feet is very cold, so they actually basically have to live in the suit that actually air conditioned. Yeah, when I say cold, the ambient temperature is cold. Yeah, but the fuselage is hot. Yeah, because we are flying at Mach 3.2, the air friction can generate hundreds of degrees. It's so hot that the pilot actually cannot stand it one. So they have to put on the suit like this, air conditioned suit. Superb, huh? This is a plane that shows that after takeoff, the SR-71 requires this in-flight refueling, because the airplane are going so fast, and every time they fly so fast, a lot of the tire exploded because the airplane was heavy, full of fuel. So eventually what they come up with a solution, the engineers say, okay, we will fuel minimum fuel. Yeah, you take off. After you take off, straight away air refueling. And then once you have air refuel, then you go on for your mission to the Russia or to wherever that you go. And this SR-71 have never landed in Malaysia, but it landed in some of the overseas countries. Yeah, it did landed in some of the overseas countries, but it requires a lot of in-flight refueling. Yeah, because it consumes a lot of fuel. A total of 6 fuel tanks. Yeah, it actually the fuel is not actually stored in the wing. For those of you who came from the aerospace industry, you will know most of the airplanes that we have, the fuel are actually stored in the wing. You know, the 747 fly for 12 hours to London. Where do they store the fuel? They store it in the wing. They store it in the horizontal stabilizer. But this SR-71, they store it on the fuselage. Yeah. Why do they store in the fuselage? Number one, there's no other space. Number two, the fuselage will be heated up, and that fuel will be the heat will be used to heat up the fuel before going into combustion. Yeah. Now this is a graph of the temperature. Yeah. And they fly at Mach 3.2. The material they use to build this SR-71 has moved from steel to titanium. Remember just now I said X1 is made of a steel alloy. We cannot put steel alloy on a SR-71 because it will become too heavy and not practical. So they came up with a new alloy. They call it the titanium alloy. And the titanium alloy is able to take a lot of very high temperature, yeah, as good as the steel, but then it is very light. It is very light. So majority of the plane, of this airplane, fuselage and all those are actually made of titanium. Why? Just look at the temperature here. At the nose itself is already 300 degrees centigrade, 3 times the heat of our water boiling temperature. Now, if you look at the cockpit area near the window here, if you can see here, it is 327 degrees C. Remember I said just now, even the pilots has to wear an air conditioning suit. It's because of this heat. It's because of this heat. And if you go towards the tail, especially near the engine exhaust, it is 648 degrees centigrade. On the skin itself, temperature is so high. The only way the engineers can overcome this problem is at the time use a titanium alloy. 93% of the skin uses the titanium alloy. Okay, a quick comparison between SR-71, yeah, and also the Russian also make the what they call it, the jet as well, but then the speed, they are still not as good as the SR-71. Then the Sukhoi technology or the MIG technology still has a lot of weakness, yeah. Now, the manufacturing process on this SR-71 actually has a lot of difficulty. Yeah, you know, the what they call it, the material used are very hard. Yeah, titanium are very, very hard. So it is impossible to forge the parts, and also you have to your machining rate is only 5% compared to the aluminum alloy. Yeah, if you think about let's say about 100 hours to machine one aluminum alloy, it will only achieve 5% of your output compared to the aluminum alloy. Yeah. Inspection method process, the engineers had to come up with a new inspection methods, new testing process, and also new quality control and manufacturing process. That itself, it is another leap of advancement of the engineers, engineers and the technologies. It uses a black paint, because of to radiate heat. You see the blackbird is always a color in black. Why? Because it actually used to radiate heat. This is the alloy that I mentioned, of titanium alloy A-11080, 5% aluminum plus 2.5% tin. There's also another one that's B120 VCA, vanadium, chromium, and also aluminum. Of course, this kind of materials, how we're going to use it is how we're going to produce it. It is proprietary. Nobody knows it, how they produce it. But generally, we know that titanium has been used extremely widely, widely on the SR-71, even in the Concorde as well, even in the Concorde. I mentioned just now the high temperature zones, especially in the exhaust area. We went up to about 650 degrees centigrade. Nickel alloys are being used, nickel alloys are being used at those heated areas. So as engineers, you have to know the strong thermodynamics, the principle of heat, the movement of the heat, and all those. The other part that they started to use, at that time, the composite materials, you can see along the edge of the SR-71, it is actually made of silicon asbestos, and fanny kind of composite parts. Silicon, it is it can withstand this construction can actually withstand the temperature up to 400 degrees centigrade. That is actually being used. So composite parts has been used, applied on the airplane since the 40s and the 60s. Widely used. Now today we have very advanced composites, the 787 and also the Airbus A350. They use fuselage, no more metal. They use composite materials, to build these modern planes. Another view of the SR-71, very majestic, very beautiful. Now let's talk about engine. The engine you mentioned just now was rocket engine, but this one is a Pratt & Whitney J58 turbojet engine. It is a pure turbojet. It's not a turbofan engine, which means that the air going into the engine will all be burned up only during the afterburner stage. When they want to apply the max speed, you can see the pipings here. These are the pipings that actually uses the bypass air that don't go into the core of the engine anymore. They go straight into the exhaust, and then where the afterburner will be used to actually ignite the fuel to continue the max speed of 3.2. Even that engine also, it is highly technical, but it is all mechanical, mechanical engines, mechanical fuel computers, fuel control unit. This is also another view of the engine. If you remember just now, I mentioned about this cone here. This cone here are actually moved according to the speed of the airplane. The main purpose of this cone here is to reduce the shock wave interrupting of the airflow into the engine. These data about the shock wave, learning of the shock wave came from the Bell X1, understanding of the shock wave effect on the gas turbine engine. Especially on the high speed. Start the engines. They have a starter. And this starter is actually made of car engines. The car engines are being modified, installed on this cart, and then they're going to use this cart to actually start and spin the engine up. Spin the engine up so that actually it can start the engine on ground. Another view of the JT58 engines. This is actually a view to show you that Just now, the rocket engine, they use oxidizer, oxygen, and also alcohol. Yeah. And this engine actually uses JP7. It actually has a very low vapor pressure, and actually it has a very high flash point. So even if you light a cigarette and throw it on this JP7 kerosene fuel, it will not light up. So how did they actually light up the engine? The engineers came up with a special chemical. They call it triethylborane injection. This triethylborane is basically an explosive ignition. The moment it touches air, it will explode. And that is the one that the engineers use to light up this JP7 engine. Yeah, marvelous, right? So we have this high-speed supersonic speed. We have cutting edge materials, remember, titanium alloys. It has actually have a monocoque structure, multi-spar, and then fuselage and the fairings, the chin on the side. You can see on this plane here, on the side here, those are also lift generating device, not only on the wing. Yeah, we used to study only on the wing, right? But this chin here are also aerodynamic lift device, which means that it can actually support 20% of the aircraft total lift, which is quite significant. Yeah, quite significant. And then they have actually came up with chines, yeah, chins that actually reduce the trim drag. And then vortices from these chins, yeah, actually improve the directional stability of the plane, especially as the airplane increases the angle of attack. And also the chin actually provides a convenient housing for the wirings inside the aircraft. Remember, this airplane is a spy plane. I think a few thousands of kilos of camera equipment are actually being put on board of this airplane. Yeah. However, in 1968, yeah, despite the marvel of this technology, in 1968, the President Lyndon Johnson, yeah, issued an instruction that all molds in 1968, all molds and tools used to build the SR-71 to be destroyed. To be destroyed. That is actually from the President's office, so that the airplane can never be built again. So for other people to actually imitate, you know, or emulate this design again, it is very, very, very difficult. Very, very difficult. So the SR-71 generally will be lost. Yeah, the technology availability is actually lost. Nobody can actually take it anymore. You can see the airplane, but if you try to build it again, you will have a lot of difficulty. Yeah, the reason is because they do not want the enemy to actually get the technology. So a bit sad, because to me, I think advancement of technology also advancement of power and authority. I hope our Malaysian can actually move towards that direction, where we have a lot of engineers, technologies, and technicians to actually together help to build the strength of the nation. Yeah. Now this is my last slides. I said that engineers shared the same feeling. I also feel what Kelly Johnson has said, and this will be my concluding slides. He said, Kelly Johnson said, my work has always been exciting to me and still is. Same for me, yeah. Even though I've been in the aviation, aerospace, engineering industry for the last 33 years, I also feel the same. Has always been exciting, and it still is. Very serious study. Yeah, we do a lot of studies. Very demanding, but it has always been a joy. You know, we actually engineers, the moment we find out something, the moment we learn something new, it is a joy inside you. There's so much of satisfaction inside us that actually you just find that this job is, you can't even believe that we are being paid for the job. Do you know that as an engineer, you come to a stage where there's so much excitement and fun that, wow, you know, we are even being paid for the job, you know. So that is the joy of an engineer, yeah. I literally love aerodynamics, mathematics, physics, machinery, and all the tools of my trade. Yeah, same as me. I consider myself very fortunate to have lived my professional life doing exactly what I always wanted to do. This is actually Karen Johnson's. I think and I hope all of us who take up engineering job engineering role will have this kind of we share this kind of feelings, especially in our job as an engineer. Okay, I wish all of you good luck, and thank you for all the for your attention. I actually open up before I open up these question and answers. Probably I just share with you here in the picture. This is another subject of its own. Yeah, will you be the next engineer? This is my question here. If you look at the airplanes that we have come, this is actually the spaceship one from the Virgin Galactic, which actually flew Mach 3.2, yeah, on a personal, not at the government. SR-71 is still operated by the government, yeah, but this is actually privately operated at Mach 3.2. You can see all the development stage by stage from Wright brothers until now, where we can public can actually fly at Mach 3.2, yeah. And I hope you will be the next engineer to continue our humanitarian, yeah, humanitarian cause, yeah, for the good cause. Thank you, and I will pass back the floor to Dr. Ong. Thank you so much.
Thank you, IR Ricky. Now we will go ahead and take some time for questions. Just a reminder, please type your questions in the chat box. Any questions from the participants? Okay, while waiting for the questions, participants may fill out the sign up form and feedback form after the webinar. Now we would like to take a group photo with everyone in this webinar. Dear participants, please turn on your camera and stand by. Okay, so is everyone ready? So we are going to take our first picture. So ready? 3, 2, 1, smile. Okay, let's take another freestyle. 3, 2, 1, smile. Thank you, everyone. IR Ricky, I think there is one question shared in the chat box. It's by Vincent Lim. Would you like to answer the question?
Okay, SR-71 destroyed, but technology has been retained to move to the next technological advancement. In a way, yes, even though the mold has been destroyed, but the technological experience by the aircraft designers, the engineers, has been able to actually move to the next level of supersonic. Yeah, we are talking about hypersonic now. If you look at the, if you have watched the Top Gun movie, Maverick, yeah, at the initial stage, if you remember, there was an airplane being taxi out and it flew at the Mach 10, yeah, Mach 10. That actually is called a dark star. The dark star, rumors say, yeah, it actually has been developed, still in the developing stage. I believe many of the technology that is incorporated into that airplane that is flying at the speed of capable of up to 6 or 7, many of the technology will be actually be either incorporated or evolve from the SR-71. Definitely they need it. Definitely they need the information, even though the mold has been destroyed. Okay. Hope I answer your question, Vincent. Will you be the next engineer? Will you be the next engineer to actually develop further? I hope you all will. Any other question? The challenges are, what were the challenges to overcome the barrier if sound? You mean the sound barrier? Of sound, okay. What are the challenges to overcome the sound barrier? Yeah. Okay, the first thing is actually the shock wave. That is actually the shock wave. How are you going to control the shock wave? Now, the transonic speed, yeah, about 0.9 to 1.2 or 1.1. During when the airplane fly at that speed, it's very hard to predict the airplane. It's very hard to predict how the airplane can actually behave, whether you apply the elevator, whether the airplane can pitch or not. Sometimes it can, sometimes it cannot. So the trick is, don't stay at this transonic. Go ahead further than the transonic. Once you're above 1.3, 1.4, then the shock wave will become much more stable. Once the shock wave is stable and doesn't move around, then you can actually start to put in the controls to control the plane. That is one thing. Whether you are able to trim the airplane, whether you are able to roll the airplane, whether your structure is able to take up the roll load, yeah, the G forces that is actually come along at the Mach 1 above Mach 1.3. All these are predictable already. But during the transonic speed, it is very unpredictable because there's a lot of factors in it that actually causing it to be the airplane to respond or behave differently. And because of this inability to actually determine, so a lot of the planes actually during testing stage actually crash with the pilot died. That is one area. The shock wave controllability of the airplane. That's number one. Heat, we can easily overcome because of the material that we can use. We can predict at what Mach number what is the speed. The difficult is actually the shock wave. The other third one that actually the challenges that we face is that if we were to commercialize this supersonic or high supersonic plane, we have to find a way to actually overcome the sonic boom. Yeah, the sonic boom. The sonic boom is actually very destructive one. So if it is like a loud explosion, especially when the airplane fly at the above the speed of sound, that actually is also a challenge. That is why the Concorde, even though the Concorde is one of the best supersonic commercial plane, but in a lot of countries, they don't allow it to fly. Why? Because of the effect of the sonic boom. You know, sometimes it's detrimental to human being, it's detrimental to our equipments, you know. So when the Concorde flew last time, flying at a Mach 2 or 1.8 and all those, they can only fly at that speed over the ocean. Once it comes into a land area, the authority or the government prevents it, you know, ban it, bar it from flying at the sonic speed. So those are the challenges, yeah. Some of the challenges are. The other challenges, like for example, if you're hit, because you're flying at the sonic speed, right, or above sonic speed, the expansion of your material, you know, some goes up to 6 inch, sometimes even go to 8 inches or 1 feet. How are you going to make your connections, your joints, and your structures all, you know, do not experience undue excessive stress? All these are the challenges. There's a lot of challenges. So it's very interesting, yeah. Thank you, Vincent. Any other questions? I don't know how many participants are here today, but I really hope that some of you actually continue on the legacy of the nobility of the engineer, yeah? Nobility of the engineering profession. Any more questions? I'm actually based in Subang, Vincent. Our engineering, aircraft engineering company is actually based in Subang, and I've been there for the last 17 years. Yeah, I started off in Malaysia Airlines, and then went into EVA Air as a station engineer, and then went into KLM, and then in 2006 I came back to Subang to set up the engineering services company for corporate jets, yeah, for private jets. A lot of fun, a lot of fun. No more question, Dr. Ong?
Thank you, IR Ricky. Is there anything that you would like to cover before we wrap up?
Probably what I would like to share with the participants here, especially for the students. In Malaysia, we are still shortage of a lot of engineers. A nation's progress, if we look at the China, why China is able to progress so fast? It is actually because of their engineering and technological capability. So for a nation to actually to progress, we need a lot of engineers, we need a lot of engineering technologies and a lot of engineering technicians. Not everybody can become an engineer, but if your results, are good enough, and then consider taking up the engineering profession. At the moment now, only 20% of the Malaysian students are actually taking up science subject, or engineering subjects. Only about 20%. The rest of the 80% are all going into the arts subject. And that actually, if this continue on, it will create a problem to our country. Actually, I hope all of you consider taking up science subject, technological subject, engineering subjects, so that we can actually help together to build our nation. That is my only hope. Thank you, Dr. Ong.
Thank you, IR Ricky, for the insightful webinar. Dear participants, please join us for e-KLESF award ceremony at 12:30 p.m. later. Thank you, everyone, and stay safe.
Thank you. Bye-bye.
Bye-bye.